So welcome to my channel, and this is just a re-upload of the first video that I made, which is ocean acidification, but there was like a slight audio problem with that, so let's get going. Let me share my screen. Okay, let me get to the first slide. So ocean acidification by me, yay. This is what ocean acidification is like in a sense, but like I can explain the simplified, although not much, but just breaking it up. So first of all, burning of fossil fuels increases carbon dioxide levels from 285 ppm to 385 ppm in 2006. Average ocean pH is how basic or acidic a liquid is, has decreased since the Industrial Revolution, which is like, yeah. The reason ocean pH can still maintain a stable level is because there is a substance called a buffer. A buffer is a substance that can prevent a sudden change in the alkalinity or acidity of a solution. The buffering action of carbon dioxide lets the ocean maintain a relatively stable HP. So moving on, the ocean pH on the surface has a pH about 8.5 because carbon dioxide dissolves in the top few layers of the ocean. Middle depth water has a pH of 7.5 to 77, because there is no photosynthesis there to break it down and dissolve the carbon dioxide, so the concentration of carbon dioxide is higher. Small changes in ocean pH will have profound effects on calcifying organisms. A reduction of ocean pH will also increase the concentration of dissolved copper, zinc, and other toxic metals. 30% of world's carbon dioxide doesn't go into the air as it goes into the ocean. Since the beginning of the industrial era, the ocean has absorbed some 525 billion tons of carbon dioxide from the atmosphere, presently about 22 million tons per day. At first, scientists thought this might be better because it leaves less carbon dioxide in the air to warm the planet. But in the past decade, they've realized that this slowed warming has come at the cost of changing ocean's chemistry. When carbon dioxide dissolves in seawater, the water becomes more acidic and the ocean's pH, a measure of how acidic or basic the ocean is, as I already explained, drops. Even though the ocean is immense, enough carbon dioxide can have a major impact. In the past 200 years alone, ocean water has become 30% more acidic faster than any known change in ocean chemistry in the last 50 years. Scientists formerly didn't worry about this process because they always assumed that rivers carried enough dissolved chemicals from rocks to the ocean to keep the ocean's pH stable. Such a relatively quick change in ocean chemistry doesn't give marine life, which has evolved over billions of years in an ocean with a generally stable pH, much time to adapt. In fact, the shells of some animals are already dissolving in more acidic ocean water, and that's just one way that acidification may affect ocean life. Overall, it's expected to have dramatic and mostly negative impacts on ocean ecosystems, although some species are finding ways to adapt to the changing conditions. When it comes to carbon emissions, people tend to focus on what happens in the atmosphere and on land. But about a quarter of carbon emissions dissolve in oceans, lowering the water's pH and causing ocean acidification. That could affect what kind of seafood is on the menu. Like oysters and clams, like they're vulnerable because like they have shells. Like lobster and crabs, they're not that much affected because like their shells are different. So species' abilities to regulate internal pH may be a driving force from the University of California, Los Angeles hypothesis in its last paper. The research used materials from a previous exhibit that set up tanks with various acidity levels to raise a range of organisms, including crabs, corals, oysters, urchins, and shrimp. The tanks had various carbon dioxide levels which coincide with acidity, ranging from 400 to 2,850 parts per million. That was what ppm stood for in the first page. So yeah, that is from approximate current levels from an extreme but possible level within the next 100 years. Eagle analyzed the chemical composition of their shells using an isotope of boron that tracks with pH, which is an eagle is just a scientist. So I just got this from a website. In some organisms, the hypothesis held up well. So yeah, and the ability of organisms to buffer internal pH closely reflected how they grew up in response to changes in internal pH. Species such as oceans and coral were able to regulate internal pH well and were not adversely affected except at the highest acidification levels. Others, including lobsters and blue crabs, were not only able to regulate pH, but also grew shells faster and larger when more CO2, carbon dioxide, whatever you want to call it, was present. However, some species, including commercially important oysters and other mollusks, faced poorly and had a hard time forming robust shells in acidic waters regardless of internal pH regulation. This could prove problematic for many eateries, raw bars, and cocktail lounges that have these items on their menus. A coccolithophore is a unicellular phytoplankton. Coccolithophores rely on calcium carbonate, which is there is less because if the pH level rises, then the more hydrogen ions there are. More carbon is needed to make hydrogen ions, so there is a limited supply of calcium carbonate. Also, many shell-based organism skeletons will dissolve, but that's that. So, coccolithophores create a chemical that produces clouds, and reduction of coccolithophores will then reduce clouds and will reduce Earth's reflectivity with less clouds and will lead to more global warming, which has started by pollution, which leads more to more CO2, which will go into the ocean, which will cause more ocean acidification, which leads to a cycle. So these are my sources. The end of the world. Yeah, you get the point. So anyway, yeah. Sorry for the background noise. And that is all for today's video. So be sure to subscribe and like, and if this gets to like 50 views, like I can make more videos.